The method of partial fraction decomposition. Okay, so let's begin our discussion on the method of partial fraction decomposition. This slide serves as an introduction to the entire technique. As you know from your previous work with integrals, sometimes we come across functions that are expressed as one polynomial divided by another. These are called rational functions. Often, these rational functions are quite complicated, and standard integration formulas just aren't enough to solve them directly. That's where partial fraction decomposition, or PFD as we'll often call it, comes in. PFD is essentially an algebraic tool that allows us to take a complex, what we call a proper rational function, and we'll define proper shortly, and break it down into a sum of much simpler fractions. Think of it like this. You've probably spent time learning how to combine simple fractions into a single, more complex fraction by finding a common denominator. Partial fraction decomposition does the opposite. It takes that complex fraction and splits it back into its simpler parts. And why do we do this? Well, those simpler fractions are much easier to integrate. They usually lead to integrals that can be solved using basic rules like those involving logarithms or inverse trigonometric functions. So, PFD is a crucial technique for tackling a wide range of integration problems. In the following slides, we'll break down exactly how to perform this decomposition step by step. Conceptual analogy. Okay, so we've just discussed what partial fraction decomposition, or PFD, is a way to break down complicated rational functions to make them easier to integrate. Now, to really solidify this idea, let's look at an analogy. Think about a situation outside of mathematics, specifically from finance. Imagine you have a single $100 bill. In our context, this $100 bill represents that complex rational function we're trying to deal with, something that looks intimidating as a whole. Now, that $100 is a single unit of currency, right? But it's made up of smaller denominations. You could have two $50 bills, or 10 $10 bills, or even a mix of different smaller bills. These smaller denominations are like the partial fractions, the simpler fractions we get after we decompose the original complex function. Let's take it a step further. Imagine you're trying to buy something from a vending machine, but this vending machine only accepts $10 bills. You can't just stick a $100 bill in there. You have to decompose your $100 into $10 bills, 10 of them in this case, to be able to make your purchase. That's exactly what we're doing with PFD in calculus. We're decomposing a complex integrand, the function inside the integral, into simpler parts. These simpler parts are the partial fractions, and they allow us to actually solve the integration to make the payment, completing the integration process, possible. So, keep this analogy in mind as we move forward. It helps illustrate why we bother with this technique. In the next few slides, we'll start looking at the specific steps involved in actually doing the decomposition. Step-by-step process of decomposition. This slide is a bit of a roadmap. It simply states that the method of partial fraction decomposition isn't just a random collection of steps, but a carefully ordered logical process. Think of it like a recipe. If you skip steps or do them out of order, you likely won't get the desired result. Okay, so we've talked about what partial fraction decomposition is, how it helps us break down complex fractions for integration, and we've even used an analogy with money to help visualize the process. Now, let's talk about how we actually do it. We're going to move through a series of steps, and each step builds upon the previous one. In the following slides, we'll detail each of these steps, starting with ensuring our fraction is in the correct form, what we call a proper fraction, then factoring the denominator, figuring out the basic structure of our decomposition, and finally, solving for the unknown constants. So, keep this slide in mind as we go forward. It's a reminder that there's a method to the madness, and following the sequence is key to successfully applying partial fraction decomposition. We'll be building on this foundation as we move into the more detailed steps in the coming slides. Verify the function is proper. Okay, so let's move on to a crucial first step before we even begin the partial fraction decomposition process. As we discussed earlier, partial fraction decomposition helps us break down complex fractions into simpler ones, making them easier to integrate. But there's a condition that needs to be met first. This slide focuses on ensuring our rational function is what we call proper. Now, what does that mean? A rational function is simply a fraction where both the numerator and the denominator are polynomials. We represent it generally as p of x divided by q of x. A rational function is considered proper if the degree, that is, the highest power of x in the numerator, p of x, is strictly less than the degree in the denominator, q of x. So, if the numerator has a highest power of, say, 1, the denominator must have a highest power greater than 1, like 2 or more. Think of it like this. The denominator needs to be bigger than the numerator in terms of its polynomial degree. Now, what happens if our function isn't proper? What if the degree of the numerator is greater than or equal to the degree of the denominator? That's where polynomial long division comes in. If we encounter an improper, rational function, we must first perform polynomial long division. This will allow us to rewrite the function as a polynomial, a regular expression with terms like 3x squared plus 2x minus 1, plus a proper rational function. This proper rational function will then be the one we can decompose using the partial fraction method we're learning. Essentially, long division helps us remove the part of the numerator that's too big relative to the denominator, leaving us with a proper rational function that we can then work with. This is a really important preliminary step, so make sure you understand it before moving on. In the next slide, we'll look at how to factorize the denominator, which is the next key step in the process. Factorize the denominator. Okay, so we've talked about why we do partial fraction decomposition to make complicated integrals easier, and we've seen a basic analogy to help understand the idea. We've also started outlining the steps. Now, let's dive into the second crucial step, factorizing the denominator. As you can see on the slide, before we can actually do the decomposition, we need to completely factorize the denominator, which we've denoted as q of x. This means breaking it down into its simplest possible real factors. Think of it like simplifying a fraction. You want to express it in its most reduced form. Now, what do we mean by factors? Well, there are two main types you'll typically encounter. The first is a linear factor. This is simply an expression of the form ax plus b. Remember, a and b are just constants numbers. For example, something like 2x plus 3 or x minus 5 would be linear factors. The second type is what we call an irreducible quadratic factor. This is a quadratic expression, meaning it has an x squared term of the form ax squared plus bx plus c, again with a b and c being constants. The key word here is irreducible. This means that this quadratic expression cannot be factored further into real linear factors. You might have tried to use the quadratic formula and found that the discriminant, that part under the square root, is negative. If that happens, you know you've got an irreducible quadratic. So, to recap, we need to break down the denominator q of x into a combination of these linear and irreducible quadratic factors. This is essential because the form of our partial fraction decomposition, how we split up the original fraction, will depend directly on these factors. We'll see this in the next slide when we talk about assuming the form of the decomposition. Think of it like building with Legos. You need to know what basic blocks you have, the linear and quadratic factors, before you can start assembling them into the final structure, which is our partial fraction decomposition. Make sure you're comfortable with factoring techniques before moving on, as this step is foundational. Assume the form of decomposition. This is where the factors of the denominator come into play. We build the form of our decomposition based on those factors. We introduce unknown constants. We usually use letters like a, b, c, and so on, because these are the values we'll eventually solve for. Let's look at the different cases. First, if we have a distinct linear factor, something like x minus a in the denominator, we add a term of the form a divided by x minus a. So, for example, if we had a factor of x minus 3 in the denominator, we'd add a term a divided by x minus 3 to our decomposition. Now, what if that linear factor is repeated? For instance, if we have x minus a raised to the power of n, meaning it's multiplied by itself n times, then we need n terms in our decomposition. It looks like this. A 1 divided by x minus a, plus a 2 divided by x minus a squared, plus a 3 divided by x minus a cubed, and so on, all the way up to a n divided by x minus a raised to the power of n. Each power of the repeated factor gets its own fraction with a corresponding unknown constant. Finally, we might encounter irreducible quadratic factors. These are quadratic expressions like x squared plus bx plus c that cannot be factored into real linear factors. For each of these, we add a term with a linear numerator, bx plus c, divided by the quadratic factor. So, it would be bx plus c divided by x squared plus bx plus c. Notice the numerator is linear, not just a constant. Okay, so we've established how partial fraction decomposition works in principle, and we've already checked if our function is proper and factored the denominator. Now, this slide details the crucial step of assuming the form of the decomposition, essentially, guessing what the simpler fractions will look like before we solve for the unknowns. Think back to our analogy of breaking down the $100 bill. We need to figure out how many of each denomination, or in our case, how many simpler fractions, we'll need to add up to get back to our original complex fraction. Essentially, we're building a sum of fractions, each corresponding to a factor in the original denominator. The next slide will show us how to actually solve for those unknown constants, a, b, c, and so on, to complete the decomposition. But getting this form right is absolutely critical, as it sets up the entire solution process. Determine the constants. This slide details how we do that. First, once we've assumed the form of our decomposition, meaning we've written out what we think the partial fractions will look like with a, b, c, and so on as unknowns, the next step is to clear those fractions. We do this by multiplying both sides of the equation by the original denominator, which we've called q of x. This is a crucial step because it eliminates all the fractional terms. Think of it like getting rid of denominators in a regular algebraic equation. After multiplying, what remains is an identity. That just means the left side, which was our original function p of x divided by q of x, now exactly equals the right side, which is a combination of our constants, a, b, c, etc., and the factors we got from the denominator. Essentially, we've rewritten the original rational function in a different, hopefully simpler form. Now, how do we find the values of a, b, c, and so on? There are two main techniques. The first is substitution. We strategically choose values of x that will make certain terms on the right side of the equation equal to 0. This allows us to directly solve for one of the constants. For example, if we can make a term with a in it disappear by choosing a specific x value, we can solve for it right away. The second technique is equating coefficients. This is where we expand out both sides of the equation after we've multiplied by the common denominator, and then compare the coefficients of like powers of x. So, we look at the x squared terms on both sides, set their coefficients equal to each other, and that gives us an equation we can solve. We repeat this process for the x terms, the constant terms, and so on. These two methods, substitution and equating coefficients, are our primary tools for unlocking the values of those unknown constants and completing the partial fraction decomposition. In the next slide, we'll walk through a detailed example to see exactly how this all works in practice. Okay, so we've spent the last few slides building up to this point, actually finding the partial fractions. Remember, we started by understanding why we do this, to make integration easier, and then we talked about checking if our function is proper and factoring the denominator. Now, let's get our hands dirty and solve for those unknown constants. Detailed example. Okay, let's work through a detailed example of partial fraction decomposition. This will really solidify the steps we've discussed. Here's our problem. We want to decompose the rational function 5x minus 1, all divided by the product of x minus 1 and x plus 2, into partial fractions. First, as we always do, we need to check if this is a proper rational function. Remember, a proper function means the degree of the numerator. that's the highest power of x in the top part, is less than the degree of the denominator. The numerator, 5x minus 1, has a degree of 1. If we expand the denominator, x minus 1 times x plus 2, we get x squared plus x minus 2, which has a degree of 2. Since 1 is indeed less than 2, our function is proper, and we can proceed. Next, we factorize the denominator. In this case, it's already done for us. We have x minus 1 and x plus 2, which are distinct linear factors. That means they don't repeat. Now we assume the form of the decomposition. Because we have two distinct linear factors, our decomposition will look like this. The original function, 5x minus 1 divided by x minus 1 times x plus 2, equals a divided by x minus 1 plus b divided by x plus 2. And b are constants that we need to solve for. Let's move on to solving for those constants. The first step is to eliminate the fractions. We do this by multiplying both sides of the equation by the common denominator, which is x minus 1 times x plus 2. This gives us 5x minus 1 equals a times x plus 2 plus b times x minus 1. To find a, we use a clever trick. We choose a value of x that will make the term with b equal to 0. In this case, that value is x equals 1. Substituting x equals 1 into our equation, we get 5 times 1 minus 1 equals a times 1 plus 2 plus b times 1 minus 1. This simplifies to 4 equals 3a. Solving for a, we find that it equals 4/3. Now, let's find b. We do the same thing, but this time we choose a value of x that will make the term with a equal to 0. That value is x equals -2. Substituting x equals -2 into our equation, we get 5 times -2 minus 1 equals a times -2 plus 2 plus b times -2 minus 1. This simplifies to -11 equals -3b. Solving for b, we find that b equals 11/3. Finally, we can write out the decomposed form of our function. We have 5x minus 1 divided by x minus 1 times x plus 2 equals 4/3 divided by x minus 1 plus 11/3 divided by x plus 2. And that's it. We've successfully decomposed the rational function into its partial fractions. Remember, this is done to make integration much easier, as we'll see in future lessons. Also, keep in mind the common mistakes we discussed on the previous slides, like ensuring the function is proper and handling repeated factors correctly. Common mistakes to avoid. First, we have ignoring the proper requirement. Remember from earlier slides, a rational function is just a fraction where both the numerator and denominator are polynomials. Before you even think about starting the decomposition, you absolutely must check if your fraction is proper. What does that mean? It means the degree, that's the highest power of x, in the numerator, must be strictly less than the degree in the denominator. If the degree of the numerator is greater than or equal to the degree of the denominator, it's called an improper fraction, and you have to perform polynomial long division first. Think of it like simplifying a regular fraction. You can't proceed until you've simplified it as much as possible. Next, let's look at incorrect form for repeated factors. Suppose you have a denominator with a factor that's repeated, like x minus 1 squared. A common mistake is to only write a partial fraction with that squared term in the denominator. That's not enough. You need to include a term for every power of that factor, up to the highest power. So, for a factor of x minus 1 squared, you'd need to write a term with x minus 1 in the denominator, and a term with x minus 1 squared in the denominator. This ensures you account for all possible contributions from that repeated factor. Now, let's consider numerator errors for quadratic factors. Sometimes, the denominator will have a quadratic factor that cannot be factored further into real linear terms. We call these irreducible quadratic factors. When you're setting up the partial fraction decomposition for such a factor, the numerator must be a linear expression, something like b times x plus c. Don't make the mistake of just writing a constant b in the numerator. It needs to be a linear expression to match the quadratic in the denominator. Finally, we have sign errors during substitution. This is a really common, easily avoidable mistake. When you're solving for the constants, those a, b, and c values, you often substitute specific values of x into the equation to eliminate terms. Be extremely careful with your signs when substituting negative values. A simple sign error can throw off your entire calculation, so double-check your work. Okay, let's move on to slide 9. This slide highlights some common pitfalls students encounter when performing partial fraction decomposition. Paying attention to these will save you a lot of frustration. Okay, so those are the main things to watch out for. Remember these common mistakes, and you'll be well on your way to mastering partial fraction decomposition. Now, let's move on to the final slide where we'll summarize the key takeaways. Key takeaways. First, let's talk about the purpose of this whole technique. Partial fraction decomposition, or PFD as we've been calling it, isn't just an algebraic exercise. It simplifies complex rational functions, that is, fractions where the numerator and denominator are both polynomials, into a sum of simpler fractions. And why do we want to do that? Because those simpler fractions are much easier to integrate. Remember from our introduction, this is often a necessary step when tackling certain types of integrals in calculus. Next, we have a crucial prerequisite. The rational function must be proper. Now, what does proper mean? It means the degree of the polynomial in the numerator, that's the highest power of x in the top part of the fraction, must be strictly less than the degree of the polynomial in the denominator, the bottom part of the fraction. If it's not proper, meaning the numerator's degree is greater than or equal to the denominator's degree, you absolutely must perform polynomial long division first to reduce it to a proper fraction before you can apply PFD. Don't skip this step. Now let's consider the dependency. The way you decompose the original fraction, that is, the form of the simpler fractions you create, isn't arbitrary. It completely depends on how the denominator factors. Remember, we spent time factoring the denominator into linear factors like x minus and irreducible quadratic factors. The types of factors you find dictate whether you'll have terms like a over x minus, a or bx plus c over a quadratic expression. Finally, the goal of all this work. We introduce unknown constants. We usually use letters like a, b, c, and so on, and our job is to find the values of those constants. The values you find for a, b, c, etc. must be such that when you add up all the simpler fractions with those constants plugged in, you get exactly the same expression as the original complex rational function. It's an identity, meaning it has to be true for all values of x. Okay, let's recap everything we've learned about partial fraction decomposition with these key takeaways. So, to summarize, PFD is a powerful tool for integration, but it requires a proper fraction, relies on factoring the denominator, and ultimately aims to solve for constants that recreate the original function. Now that you have a solid understanding of these key takeaways, you're well prepared to tackle more complex examples and apply this technique confidently.